In this video, we'll have proof of theorem 6.5.1, which is a theorem, basic theorem on nilpotent transformation. The statement goes like this: if T is nilpotent with index of nilpotence n1, then there is a basis of E in which the matrix of T takes this form, where each Mni is a matrix of order Ni cross Ni with superdiagonal entries 1 and 0 elsewhere. And these Ni's, they should satisfy this condition that n1 should be greater than or equal to n2 greater than or equal to nr, and the sum should be dimension of V. So to prove this, basically, when we see the broad outline of this proof of this theorem, what is given to us is only T is nilpotent transformation, and what we need to bring in is basis, and we have to talk about these matrices M and I's, and we should also establish this. So broadly speaking, this is what is to be done in this in the proof of this theorem. But we'll have key points in the proof of this theorem as various claims, and we'll establish them one by one. So first we are given T to be nilpotent with index of nilpotence n1. So we have T per n1 0, T per n1 minus 1 non-zero, and because this is non-zero, we can find a non-zero vector such that the image of that under this T per n1 minus 1 is non-zero. And this is 0, and so you'll have to have Vt per n1 to be 0. Now we'll consider the vectors as first claim. V, Vt, Vt square and so on Vt per n1 minus 1 are linearly independent. Suppose they are linearly dependent, then there exist scalars not all 0 such that this. So in this, some of the coefficients are 0, some of them are non-zero. So we'll discard those which are 0 and collect only the non-zero scalars. Among them, let alpha s be the first non-zero scalar with s less than n1, because at the most that you can have it as n1, that is considered as the last one. So we'll consider our s to be less than n1, first non-zero scalar. Then this one reduces to, you will have this, because what all 0, we have not deleted them, so there will be left with only this equal to 0. Now in this, when we take t per Vt per s minus 1 out, this is what we are left with. And we proved in one of the lemmas that whenever you have unit plus nilpotent, it will be unit. Unit plus nilpotent is unit. So you have this to be non-zero. So that is unit, and this is nilpotent, we know. So this plus this should be invertible. So when we apply the inverse on both sides of this, we have Vt per s minus 1 to be 0, and this is invertible. That is the reason why you have this. So this is invertible. Now this is a contradiction. This is a contradiction to what? To the fact that to your assumption that t per n1 is 0 and t power n1 minus 1 is non-zero. So here you have s to be a number which is less than n1. So s minus 1, when you consider, that will be less than n1 minus 1. For this itself it is non-zero. Even for lesser one it cannot be 0. So we get a contradiction. So the vectors are linearly independent. We assumed the beginning that they suppose they are linearly dependent. So that assumption is wrong. So you have first claim that these vectors are linearly independent. Obviously they are n1 in number. So when we consider the linear span of these vectors as capital V1, then this V1 L of S, whenever S is a normative subset of a vector space V, we know that L of S is always a subspace. So you have this to be a subspace. That means V1 is a subspace of V, and they span V1 and they are linearly independent, and therefore they form a basis. So these vectors V, Vt and so on, Vt per n1 minus 1, they form a basis of V1. and they are n1 in number, and therefore dimension of v1 is n1. So that is what is written here. Now we claim that v1 is invariant under T. Why we need all this is, we said that basic lemma, whenever we have v to be the direct sum, then we can find the these direct sum of subspaces which are invariant. Invariant means it will induce a linear transformation. So that whenever we have this, then we have a basis in which matrix of T takes this particular form A1 etc. AK. So this lemma needs to be used here. So for which we need to have a direct sum of invariant subspaces. We have got now a subspace that should be checked whether that V1 is invariant under T. So that means we have to show that V1T is contained in V1. So for which you consider some element in this X and say that X is in V1 also. So X belongs to V1T means X is written as Vt where small v belongs to capital V1. And capital V1 being linear combination of these vectors, so we can write that as this operated by T. Now when we consider this, this is what we have. The last one will be T power n1, that will be 0. So we'll be left with alpha n1 minus 1 Vt power n1. This is n1 minus 1 alpha suffix. So again, this is a member of capital V being capital V1 being spanned by those vectors. So we have X belonging to V1. So V1T contained in V1, which says that V1 is invariant under T, and that proves our claim 2. Now we consider our V1 as V, V2 as Vt, and so on. V3 as Vt square and so on. Vn1 minus 1 as Vt power n1 minus 2. Vn1 as Vt power n1 minus 1. So they are basis of capital V1. Next, V1 being invariant under T, it will induce a linear transformation. V1 is invariant under T, it induces a linear transformation restricted to V1, which we denote as T1 on V1. So we'll have to obtain the matrix of T1, right, in this basis V1 etc. up to Vn1, which means only if we write in this form we can write out the matrix. So we consider V1T. V1T means V1 is V, so Vt. But what is Vt? Vt is V2. So only this vector V2 is there, the rest are not there, so supply them, it's 0. Similarly, V2T is VTT, because V2 you have taken as Vt, so VTT, which is Vt square, but Vt square is V3. V3 is present, the rest are not there, so supply them with 0. And proceeding like this, Vn1 minus 1t, Vn1 minus 1 is Vt power n1 minus 2 operated by t, so we have this, and this Vt power n1 minus 1 is nothing but Vn1. So this is what we get, only this is present, the rest are not there, so supply them with 0. Now coming to the last Vn1t, it is Vt power n1 minus 1 operated by t, that gives you Vt power n1, but t is nilpotent with index of nilpotence n1, so this becomes 0. V0, 0 transformation takes any vector to vector 0. So none is present, so supply them with 0. So when you consider the matrix of T1, when we write it, this is what we get. So name that as Mn1, it is of order n1 cross n1. Now we are going to have the next claim. If u belongs to B1 is such that ut power n1 minus k is 0, with 0 less than k less than or equal to n1, then how we can write this u as some u naught t power k, where this u naught should be a member of this u naught, u naught should be a member of capital V1. Now, since u belongs to V1, u is spanned by these vectors. You can write that as a linear combination of this. Name that as 2. Now, applying t power n1 minus k on both sides of 2, this is what we get. And here, we don't have up to certain stage only you will have. After that, see the next one, when we consider Vt power k, here it will be alpha k plus 1 Vt power k. But we are applying on both sides this t power n1 minus k. So that means this k and minus k will get cancelled, giving t power n1, but t power n1 is 0. And so the higher powers, when we consider all of them, will vanish. So that means up to certain terms only that you have. That means here you have alpha 1 Vt power n1 minus k, and up to this it will be there. So that is what is written here. Now ut power n1 minus k is 0, so this becomes 0. So we have the we have the linear combination of these vectors. They form, see, whenever you have linearly independent set of vectors, and when you consider a subset, whenever you consider subset of linearly independent, what you can tell about that, that is also linearly independent. Subset of linearly independent vectors is again linearly independent. So we have these vectors to be linearly independent. And so the linear combination equated to 0 should give scalar to be 0. So alpha 1 to alpha k is 0. And therefore the second equation now reduces to, you have alpha k plus 1 Vt power k. From this onwards you will have all the alpha 1 to alpha k is 0. So only from here onwards that you have. So it is alpha k plus 1 Vt power k plus and so on. So when you consider t power k, when you take that out, what we have is alpha k plus 1, this one, alpha k plus 1 v, in fact vi, plus and so on, the rest you have as such, t power k. But this is again a member of v1 only, linear span of those vectors. So name that as say some u naught. What is u naught? It's a member of v1. So u is u naught t power k. Whenever we have this to be true, you have u being rewritten as u naught t power k. This is needed in proving the next claim. So 0 less than k less than or equal to n1. You cannot exceed this n1, right? That is the index of t. Now, a claim 4, which is also given as lemma 6.5.4, we need to show that there exists a subspace W of V invariant under T such that V is the direct sum of V1 and W. So to prove this, we shall take W to be a subspace of V of largest possible dimension such that V1 intersection W is singleton 0 and W is invariant under T. So whenever you consider W to be of largest possible dimension, which is a subspace of V, we have the intersection with V1. The intersection of W with V1 should be singleton 0. What is told about W? It's a subspace of V with the largest possible dimension. Right. If I'm able to prove, see, our aim is only to establish this, of which, when how to prove that V is the direct sum of V is the direct sum of A and B. We know that this is true if and only if V is equal to A plus B and A intersection B is singleton 0. This is established in UG itself. So, so if we have this, then everything will be fine. So suppose not. We know that V1 to be a subspace, W to be a subspace, so V1 plus W must be contained in V. Suppose not means what is not true? We don't have V to be contained in V1 plus W. We don't have this to be contained. So, which means there exists an element Z in V, but not in this. If we have this to be true, then there ends the matter. If not means I have an element here, but I don't have it here, right? So, since t power n1 is 0, with 0 less than k less than or equal to n1, we are going to have z t power k belonging to v1 plus w. Z t power I belongs to v1 plus w for I less than k. It does not belong to. We shall have for this part alone, because just like that, when we look into this, it may not be clear. So we shall have an illustration for this statement alone. With simple example, suppose I consider for I less than k less than or equal to n1, is it does not belong to v1 plus w, is it t power I does not belong to v1 plus w, but this. So what is the meaning of it? Can it really happen? So that is what we want to just check with this simple example. We consider V to be R4. So obviously dimension of V is 4. We shall take the basis elements as V1, V2, V3, V4. And let's suppose our T is defined in this way. Then we can easily check that T is linear transformation and matrix of T is this. And this is also nilpotent. So matrix nilpotent means corresponding transformation T is nilpotent. We shall take V1 to be span of V1 and W to be span of V3, V4. Then it can be easily verified that our V1 and W are invariant under T. Now we'll consider Z to be V2. So this your Z does not belong to V1 plus W, because in V1 you don't have V2, in W also you don't have V2. So Z does not belong to this. But how about ZT? ZT, when we consider, it is V2T. V2T is V3, and that is present in W. So you don't have Z in V1 plus W, but ZT belongs to V1 plus W. Now, in the same way, suppose I consider Z to be V1 plus V2. Then definitely, because V2 is not there, it is not in V1 plus W. When you apply T once, what you get is this one. So here you have Z alone does not belong to this, but T power T itself as a member of this is belongs to. So T will belong to, because Z when you consider as V1 T plus V2T, V1T is 0, V2T is V3, V3 is present here. So we have this, and is it T square naturally? That is also a member of V1 plus W. So for some I less than K, Z does not belong to V1 plus W. Then T power I does not belong to V1 plus W, but T power K will belong to V1 plus W. So not higher values of I that we have considered, only with I equal to 1 only we are getting. Maybe if we consider some other example, we may have all. Yeah. This one doesn't belong to, and but this one will belong to. Like that, we can have. Just to understand the meaning of it. All this need not be written in the examination. Just to know whether such a thing is possible. Right now, so now we are going to establish the subdivision 1 and 2. For some u naught in V1, Z1 when we write it as Z minus u naught, we can prove that Z1 T power M belongs to W for M less greater than or equal to K, and Z1 T power I does not belong to V1 plus W for I less than K. All these two we are going to establish. So we are going to consider this ZT power K belonging to V1 plus W, this is known to as, and T power K is equal to U plus W, with U belonging to V1 and W belonging to capital W. Being a member of V1 plus W, it can be written in this way. Now we consider T power N1. We know that T power N1 is 0, so this becomes 0. So 0 equals this, and this is rewritten in this way. And T power K is replaced by U plus W. So by the homomorphism condition, you have this. And since both V1 and W are invariant under T, U T power N1 minus K should belong to V1. And because U belongs to V1, U T power N1 minus K should belong to V1 only. And similarly, W invariant, so you have this also belonging to W. So since both V1 and W are invariant under T, you have this to be true. And you know that V1 intersection W is singleton 0. So that means this one is present in V1. So when you take it to the other side, it is something like this. ut power n1 minus k is equal to minus wt power n1 minus k. This is as such belong to v1, and this being equal to this which is in w, this one belongs to w also, so it is in the intersection. So but this is nothing but singleton 0, and so you have ut power n1 minus k to be 0. Now we already had in claim 3 that whenever we have this to be true, we can write our u as u naught t power k for k less than or equal to n1, k positive less than or equal to n1. Therefore, z t power k we can have here z t power k. When we consider, we can write it as u plus w, where u is replaced by u naught t power k plus w that we have as such. So taking this to the other side, z minus u naught t power k is w. So this is what we have up to this. We have z t power k. We have z t power k to be u plus w, of which u is nothing but u naught t power k. That when it is taken to the other side, that's what we get. And we shall take this as some z1. So that z1 t power k, which is equal to w, is a member of capital W. Since w is invariant under t, z1 t power m belongs to w for all m greater than or equal to k. W is invariant under T, so you can have for all m greater than or equal to K this. So proving one, what was our first subdivision? Our claim is that one T power m belongs to W with m greater than or equal to K. And the second one we need to establish. We shall consider for I less than K Z1 T power I. Z1 is nothing but Z minus U naught. So homomorphism, T is a homomorphism, so you can write like this, is it T power I minus U naught T power I. This does not belong to V1 plus W. Why it does not belong to V1 plus W? Suppose it belongs to V1 plus W, say. Then is it T power I? Suppose I presume that this belongs to V1 plus W. Then we have is it T power I. When we consider this, take this one to the other side, z1 t power I plus u naught t power I. What is that? Z t power I. Right, with I less than k. You have this u naught t power I belongs to v1 and this belongs to w. So which is not true by q. What is q? You have said already in statement q that z t power I does not belong to v1 plus w for I less than k. So you have a contradiction. Therefore, this cannot be a member of V1 plus W. So for Z1 T power I does not belong to V1 plus W with I less than K. So that is also established. So we have got both 1 and 2 being established. Next is we are going to have, let W1 to be a subspace of V spanned by W and this. Now since Z1 does not belong to W, W is contained in W1, the dimension of W1 must be larger than that of W. Also, since Z1 T power K belongs to W by the first one, and W is invariant under T, W1 is also invariant under T. Now, dimension of W is maximal with that V1 intersection W is singleton 0. And here W is contained in W1. So what is the inference? You cannot have intersection of W1 with V1 to be 0. You cannot have W1 intersection V1 to be 0. Because whenever you have a subspace, we have said that W is the subspace of V with maximum dimension such that W intersection V1 is singleton 0. But here you have got another subspace whose dimension is greater than that of W. So how can its intersection with V1 be just a singleton 0? It cannot be. So W1 intersection V1 cannot be 0. So you have this. The explanation for all this, they follow from 1 and 2. And this explanation, it is because of this. All this we have mentioned already, and therefore we can find one element, say gamma, which is different from 0, which is in the intersection. Now this gamma, now I can write it as W naught plus alpha 1 Z1 plus, because gamma is in W1, because gamma is in W1, W1 is spanned by element of capital W and these vectors. Just now we mentioned W1 is a subspace of V spanned by W and these vectors. When we consider W naught to be a member of W, we can write our gamma as W naught plus spanned by these vectors. So we can always write like this. Now this gamma you have taken as non-zero vector. Right. Now we claim that not all of this can be 0. We claim that not all of them to be 0. So suppose all of them are 0. Suppose not. So then what will happen? 0. You will have all these to be 0. So gamma becomes W naught. But where is W naught? W naught is in W. And gamma is now W naught. Gamma is in V1 also. So W naught now belongs to W as well as V1. But W intersection V1 is singleton 0, we have said. This is nothing but gamma. See, when you replace them with 0 means your gamma now be W naught. So this W naught, already we have said that it is in W. So W naught belongs to W. The W naught is gamma. Gamma is in V1. So this W naught is in both W as well as V1. This W naught being gamma, gamma not equal to 0, how can an element be both 0 as well as non-zero? So that's a contradiction, right? So you cannot have you cannot have all of them to be 0. Some of them can be 0, some of them non-zero. So let us take alpha s to be the first non-zero scalar. What is yes, it is a number which is less than k. So let that be the first non-zero scalar. Then this W naught plus the whole lot now becomes, we are taking Z1 t power s minus 1 out. So we'll have, see, when you have alpha s here, it should be Z1 t power s minus 1. So when you take Z1 t power s minus 1 out, first one should be alpha s and the rest will be there. The last one, k minus 1 is present. Here k minus 1 is present. So what we do is we will add and subtract s to this. So that when you take t power s minus 1 out, you will be left with k minus s. So alpha k t minus s. So a W naught plus the whole lot, this is what we have. Now this belongs to V1. We name this as statement yes. Why it belongs to V1? You have your W naught. You have already W naught to be present in W. And the whole Z1 t power s minus 1, all this, see, this is in W. And Z1 t power s minus 1, these are all in W1. Okay, so this belongs to V, it is a member of V. All these are members of capital V. And since alpha s is not equal to 0, by lemma 6.5.2, this is non-zero. Actually, it is I. So this is non-zero. These are nilpotent. Unit plus nilpotent is unit. So you can find the inverse for this. So when you apply that inverse on both sides, let us take that inverse as R, say, so that you will have W naught R plus Z1 t power s minus 1 belonging to R is, again, see, whenever you have this to be in terms of t means this R will also be in terms of t. So W will be invariant under t and all these are invariant under t only. So when you consider this, this is we can actually have this to be in the V1. This is in V1, right? So because of this gamma you have taken as this, and that is in V1. So that part we have considered. So it is not V, what was written already is correct only. So it is when you are applying, so you will have V1R, here something operated by R, that becomes identity. So W naught R plus Z1 T power S minus 1, V1 being invariant under R must be contained in V1. So W naught R plus Z1 T power S minus 1 belongs to V1. W naught R plus Z1 T power S minus 1, that belongs to V1. So from here what we have is, this is a member of capital W. So this one must be a member of V1 plus W. So because W naught belongs to W, W invariant under R also, with S minus 1 less than K. With S minus 1 less than K. S itself is less than K. We have said already that S is less than K. We mentioned here. S is less than K. So S minus 1 still less than S. So it is less than K. This is a contradiction to statement 2. What is statement 2? Z1 T power I cannot be a member of V1 plus W for I less than K. So, but you have got this to be a member of V1 plus W with S minus 1 less than K. So that's a contradiction to statement 2. So we must have, why this contradiction arose? Because we assumed that there is an element present in, there exists one Z in V, Z not in V1 plus W. So that's a contradiction. So Z belonging to V should imply Z belonging to V1 plus W. So V is contained in V1 plus W. Already we know that both of them being subspaces, V1 plus W is contained in V. So together we get V to be equal to. So together we get that V equal to V1 plus W. Already this is true. So these two together gives V to be the direct sum of V1 and W. Now since V is the direct sum of V1 and W, and V1 and W are invariant under T. So by that lemma 6.5.1, there is a basis of V in which matrix of T is Mn1. Because for the first one we have taken it as Mn1, and uh, for the first one, it is Mn1, and the next one we do not know, that's for W. So we shall take it as some A2, where A2 is the matrix of T to the transformation induced by T on W in a basis of W. So proceeding like this. So repeating the argument used for T on V, we use for T2 on W. We can decompose W as we did our capital V. So your V becomes direct sum of V1, V2 and so on. VR you can have, or VK. If you have started with VK means K you can put, or R. But see to it that the suffix remains the same, right? So we shall check it in the statement. What is N1 up to NR only we have mentioned. So if we have NK means here you should have NK. So N1 up to NR, where N1 is greater than or equal to N2, we keeps reducing, because these being dimensions of other subspaces, and not only that, the dimensions together should give us the dimension of V. These are called the invariants of T. So if define invariants of T, and that is the definitions asked in section A, means the statement of this theorem 6.5.1 should be given. If you are asked to define invariance of a invariance of a nilpotent transformation, then you have to state the theorem 6.5.1. The N1 etc. NR in that are called invariants. They are called invariants of the nilpotent transformation T. So basis, MNIs, and this part. So these are the major steps, and with the claims 1, 2, 3, 4, we can have. Sometimes even claim 4 itself can be asked as section C question, right? So this needs practice. You cannot at the first sight get the proof of this, and especially claim 4 will be challenging. So for this part, once to know this, we have got an illustration. So now after understanding that, that proof, I mean this illustration need not be given, but for you to understand that was given. So you just you can easily remember this step right now, having got that illustration. Thank you.